Hello all, I'm a senior deep learning engineer at NVIDIA and lead our engineering efforts for PyTorch Geometric and research efforts for combining graph and language modeling. Today, I will be discussing combining graph neural networks and LLMs for RAG with PyG. I will start by teasing some results. In this case study from over a year ago, Neo4j used Stark Prime, a medical question answering dataset made by Yuri Leskovic's lab based on the Prime KG medical knowledge graph. Neo4j was able to double the state-of-the-art accuracy. The previous state-of-the-art is a pure LLM approach, so this shows that adding GNNs to LLMs has immense value when used on a high-quality knowledge graph. The baseline of comparison is a 16% accurate 7 billion parameter LLM-based agentic GraphRAG, while the new GNN+LLM solution provides 32% accuracy. The new solution consists of a Llama 3.1.8b model using LoRa with a 10 million parameter graph attention transformer. It's a type of GNN. This solution shows how much accuracy can be improved by adding a GNN for such an inconsequential parametric cost. It even significantly outperforms seemingly unfair baselines of much larger frontier models used for agentic GraphRAG. They are outperformed by as much as 1.8x. The code is open sourced on GitHub. We also wrote a blog about it together. This slide has been adopted from a 2023 talk given by the creator of PyG, Matthias Fay. He defines GNNs as models that update node representations by repeatedly transforming and aggregating representations of direct neighbors. The diagrams here explain this quite well, and I will walk through each. The top is the most basic example. We have a single layer of a GNN which computes the embeddings of any single node, in this case, node 1, as a function of the embeddings of its direct one-hop neighbors. One can think of convolutional neural networks and transformers as subclasses of GNNs, much the way that triangles and quadrilaterals can be thought of as subclasses of polygons. The diagram for the convnet shows how a convnet across pixels is the same as a GNN over a graph of pixel nodes, connected to their direct neighbors in the image. For the transformer diagram, you can see that the transformer attention layer is essentially a GNN over a fully connected graph of the tokens. In general, an n-layer GNN learns to predict over n hops of information in the graph, which makes them excellent candidates for enabling multi-hop reasoning in AI systems. This is essential since multi-hop reasoning is a key aspect of human intelligence. An example of my two-hop neighborhood is me, my friends, and all of their friends. Our research finds that GNNs can improve LLM accuracy. We believe this to be possible since GNN embeddings on graph data can provide a semi-orthogonal source of information. LLMs tend to be much larger than GNNs. A transformer layer is essentially a GNN on a fully connected graph between tokens. However, the transformer uses parameters to learn the importance of each connection, while GNNs do not need to parameterize how entities are connected, since the graph data provides this information. As a consequence, adding in GNNs has almost no effect on the total number of parameters, as we saw with the Stark Prime example. As an introduction, RAG refers to retrieval augmented generation. The most basic form of RAG we will refer to as VectorRAG. This is where you retrieve the top k most relevant docs based on KNN between the query and their embedding vectors. The diagram in the bottom right corner goes through the basic workflow. This is usually good enough when the answer requires only a single document to be retrieved. GraphRAG is a general term that refers to retrieval methods that retrieve relevant subgraphs for the query. This is generally supposed to shine when the answer requires multiple documents with related entities. Here, we have a diagram of a made-up NVIDIA org chart. The question is, who is the shared coworker between Bob Joe and Ronald Coleman? At first glance, the answer may not be perfectly obvious, even to a human, but thanks to the highlighting of the key nodes and edges, the answer becomes obvious, Arno Schwarzenegger. Using PyG, a GNN plus LLM gets the answer right, while the corresponding LLM fine-tuned the same way fails to answer correctly, even though both models were fine-tuned on the same general knowledge toy dataset. The pure LLM approach I described is generally similar to most GraphRAG workflows today, such as the one popularized by Microsoft. In school, all students read left to right, just like an LLM. But exceptional students either mentally or physically highlight key ideas and form complex relations between them in their brain. I like to think of GNNs and graphs as playing this role for the LLM in a GNN plus LLM system. On June 12, 2017, the famous Attention is All You Need paper was added to ArcSci. Just 5 days earlier, Yuri Leskovic's lab published the GraphRAG GNN, which is one of the most well-known GNNs. Since 2017, the AI industry has poured a majority of its efforts into LLMs, establishing a strong foundation to build on. In parallel, a small but strong PyG community begins to grow in academia. There was also a small group of companies capitalizing on the power of GNNs. Examples include Pinterest, Spotify, and Kumo, to name a few. The goal of this GNN+LLM work is to combine nearly a decade of parallel AI research. Our goal is to add GNNs to LLMs to advance AI systems past the current limitations of LLMs. This diagram depicts a general graph-based RAG workflow using GNNs as a prefix to the LLM's inputs. For the sake of time, I will skip going over the details, but see the QR code in the corner for a previous talk I gave at Stanford, which has all the details. In short, we retrieve a semantically relevant subgraph of the query and encode the subgraph with a GNN. This system is fine-tuned to enable the GNN to communicate with the LLM. Most RAG datasets only have unstructured text context. As such, there is often an additional task where we must convert unstructured text into a knowledge graph. Our existing PyG framework uses the simple KG format of triples of entity, relation, entity. As mentioned before, LLMs are specialized for handling unstructured text, so they are the ideal model for this task. As our solution to this problem, we created the text-to-KG class in PyG 2.7. This system consists of a combination of frontier model prompt engineering and some Python filters on top. If you look at the top image, that snippet is the current system prompt for this class. The snippet on the bottom shows how easy it is to use. In general, we should expect that combining vector and GraphRAG is always at least as good or likely better than either alone. GNNs help the LLM decoder to understand graphs, producing better accuracy. This diagram covers the fully combined workflow. As you can see, this is the same diagram from before, but I have added in a block to insert the documents retrieved by any sort of document retrieval method. Since our system is fine-tuned, the LLM should learn to reason over both sources of information. This system is seeing adoption throughout NVIDIA and across many Fortune 500 companies. See example/LLM/text-to-kg_rag.py on PyG's GitHub for an end-to-end code example. In this experiment, we measure the accuracy of a Llama 3 8B generator by using a much smarter 253B reasoning model as an LLM judge. The question-answer pairs for this test were generated synthetically using multiple chunks of text for each question. We consider the speed of light to be when we feed the generator with the exact context that was used to generate the question-answer pairs. This is what we would consider perfect retrieval. Notice how we are only 1.1% accuracy away from the speed of light. We also perform much better than basic RAG solutions. Keep in mind that we didn't do any hyperparameter tuning to achieve these results. That is, we use the same set of default hyperparams across the board. This slide covers a demo made by our PM Santosh Bhavani. He was able to upload our PyG code to Cursor in the pre-Claude Code era and have Cursor completely vibe code a graphical interface showing how easy our framework is to build upon. This is now released as an NVIDIA product. This is great for creating knowledge graphs and then manually reviewing them before using PyG to train a GNN+LLM system. Is it gonna play? It's not gonna, it might play. No, I'll come back to it at the end if it works. Our next major, at a high level, it's just a GUI, it'll generate a knowledge graph, you can interact with it, but it was built from scratch by someone without coding experience using Cursor. Imagine you give our docs to Claude Code, you can build anything. Our next major steps for this are integrations into real-world use cases internally and externally. We will also continue to refine the PyG codebase in terms of speed, usability, and accuracy. We also plan to have our NVIDIA Rapids team optimize the retrieval workflow to enable near unlimited scalability with maximum speed. Additionally, we plan to look into new retrieval techniques, such as using GNNs for the retrieval, not just the generation step. The idea of using GNN embeddings as a prefix to transformer sequence models is highly general and can be extended to many modalities. The goal of the latest PyG community sprint was to expand GNN+LLM features to support the sciences like biology and chemistry. There were 4 projects going on to integrate techniques from 3 biology papers and 1 chemistry paper using GNNs and LLMs. The general goal of these projects is to advance medicine and science and integrate general reusable APIs for GNN+LLM workflows. The sprint was finished a while ago, and check the examples out in the examples/LLM/README on the PyG GitHub or the NVIDIA container. This slide shows just one of the examples called Molecule GPT. This example enables a talk-to-your-molecule experience by combining graph modeling and language modeling to allow the LLM to better understand molecular structure. Check out the links for further details on Molecule GPT. We actually have an interesting spectrum of graph-like data. On the left side of the spectrum, we have the setting of unstructured data in the form of documents that we must parse into a knowledge graph. This setting is inherently less accurate since we rely on an AI model for this parsing. On the other side of the spectrum, we have data like molecules, hyperlinked document graphs, or relational table data like in RelBench. In this setting, we assume our graph data is highly accurate. In general, each data source will often cover different knowledge. We also know that most enterprises have multiple of these data sources. Using PyG, you could set up a separate GNN for each type of graph data source, all providing context to a master LLM, following similar patterns as discussed before. This technique could also be used to incorporate ontologies created by industry experts. As a final note, today there are 2 kinds of GNNs. The traditional kind are the message-passing GNNs. Then there are graph transformers, which are newer. See the QR code for a webinar on the topic I gave with Stanford and Kumo.ai. I'm working with the community to get more graph transformers added to PyG. My goal would be to see how these affect the accuracy of the previously discussed GNN+LLM systems. As a final note, I want to acknowledge my fellow contributors to this effort and all of the PyG contributors. The PyG community is ever growing, and contributions are welcome. As a shout out, 2 of my contributors are right up front, I guess. Thank you.